presentation. Right? I think 3 folks have already chosen their topic. There's lots of topics left. And again, if there's a topic that you're particularly interested in that's not on there, let me know and we can discuss that. We are skipping over chapters 9 and 10. Chapter 9 is atomic emission spectroscopy. We talked about atomic absorption. They're not all that different, and optical emission spectroscopy is on the list. Right? Chapter 10 is X-ray spectroscopy or X-ray techniques, and that's also on the list, both X-ray crystallography, X-ray fluorescence, that kind of stuff. So I'm going to save those for December, and both of those are neat techniques. In all honesty, optical emission spectroscopy is sort of becoming more important, more used than atomic absorption spectroscopy. And so it is starting to sort of overtake it in terms of actual instruments sold and things like that. And X-ray, of course, is a technique that's useful across lots of different disciplines. Biochemists use it for crystal structures. Art historians use it to determine sort of what kind of pigments there are. And so, X-ray, if 2 people wanted to do X-ray for December, I think that'd be okay. Somebody do X-ray fluorescence, somebody do crystallography. I think there's just so much there. But we must move on, and the semester is only so long, especially at Wofford. So we are moving into infrared spectroscopy today. Those notes are on Moodle. And I wanted to, there's one other thing I wanted to, oh yeah, the journal club is up. Let's schedule it for Friday, right? We'll do a Friday discussion. The journal club article this week is a pocket-sized infrared spectrometer. It's about the size of it's really about the size of a deck of cards. Right? It's a really small little dude. It was sort of invented and thought through for the agricultural industry. Make sure your corn has the right amount of water in it. Make sure your pig feed is getting all nutrients, that kind of thing. But the paper I uploaded is actually a food chemistry kind of paper. They are analyzing different cheeses, both with a regular old benchtop, large format infrared, as well as this pocket, and comparing the difference. I don't want you to get too deep into the statistics. They run a lot of stats to make sure that the two are similar, right? But cruise the website for the spectrometer. I posted that as well. Then take a look at sort of their techniques and what they did, and then their discussion and conclusion. I might post a couple of sort of guiding questions for this one. Because I don't want you to get too deep into the statistics, I might kind of try to point your attention at what I think is the most interesting part of the paper. I haven't done that yet, but I do plan on doing that this afternoon. Another thing I plan to do this afternoon is to record Wednesday's lecture. So we will not have class on Wednesday, but I will post another lecture from chapter 11. I don't know that I'll make it 50 minutes because golly, a 50-minute video that you gotta sit through is about as bad as sitting through this class. So I want to just make sure that, that it's more feasible, more approachable, I guess is the word I want to use. Okay. But the plan is to finish infrared this week. So between today and whatever I post Wednesday, and then after our journal club discussion on Friday, we'll finish infrared. Our exams tomorrow, UV Vis, AA, and fluorescence. Any burning questions before we get started with chapter 11? I see a couple of you have made appointments this morning. So that's fine too if you'd rather do things in private.
I have a question about the monochrometers that we were supposed to think about.
Yes.
So I've figured out like which are scanning and which are set, but I don't know if I can explain why. So that's a little bit of an issue.
So I'm going to add another question to the pile and see if it helps clarify things. Think about what wavelength it's set on.
So like when you say scanning, does that mean what do you, so I understand the set one, the fixed one, but what is the scanning one doing for us?
Well, what is set when you set one?
The wavelength.
The wavelength. So the scanning one must be scanning through wavelengths.
Yeah.
And so instead of getting data at a single point, you're actually getting your spectrum, right? You're getting your absorbance data,
Right.
emission data at
Right.
a wide range of wavelengths.
Okay. Okay, I'll think about that.
Okay. All right. Okie doke. Anything else before we jump into chapter 11? All right, let's do it to it. So infrared is where we're going. And to start us off, we need to talk a little bit about vibrations. This is what I sort of made you plug and chug in chapter 2, right? Maybe even chapter 1, way back when. And hopefully you sort of got through those equations okay. We're going to talk through those a little bit more. And so when we talk about infrared, right, remember infrared is looking at vibrational transitions. And so UV-Vis looked at electronic, infrared looks at vibrations. Do you remember what region of the electromagnetic spectrum looks at rotations?
Microwave.
That's it, Savannah, microwave. And so, you know, we have these different regions, these different energies in the electromagnetic spectrum that are sort of tuned to different transitions within a molecule. And so, of course, we can't do infrared on elements, right? Elements don't have vibrations. There are some studies of, you know, infrared on crystal lattices. And so looking at like a metal does have a crystal lattice if you have, you know, just a piece of pure metal. And so they can use infrared as a way of sort of seeing if there are impurities, because those impurities are going to have slightly different vibrations than the metal as a whole. And so generally speaking, we can't look at elements very well, but it's very good for looking at molecular structure, especially because different types of bonding will, of course, have different ways of vibrating. When we talk about vibrations, the equations that we're going to use are very physicsy, right? And so the angular frequency is omega. That looks a whole lot like a W, but I try to close my top a little bit for omega. And so the frequency, this angular frequency of the vibration, is equal to the square root of K, the spring constant, divided by mu, the reduced mass. Now this spring constant is in newtons per meter. Reduced mass has to be in kilograms to keep all of our units kosher. K is not a unit, kilogram. And so the spring constant, or how much force it takes to, in physics, lengthen a spring, to pull a spring by, well, a meter, right, Newton per meter. Of course, in molecules, we are not separating those atoms by anything close to a meter, right? But we're moving those atoms from one to another. When we think about a spring constant, almost always we think about it as one of those atoms being fixed. So one of those atoms being sort of our origin on a graph, and the other atom moving relative to it, right? There are some cases where that throws a wrench in the works, and so we have to work out center of mass equations. But generally speaking, we think about it as being fixed to a single point. This is especially true if we're talking about something like HCl, right? Chlorine is 36 times as massive as hydrogen. It is really not moving very much, right? That's like me and Nadia bouncing. I bounce. I don't bounce. She does. And so when we go to calculate these spring constants, they will be related to sort of the strength of that particular bond, right? And so if you had to guess, single, double, triple, which one of those is going to have the highest spring constant?
Single.
Caroline and Annabelle disagree.
Triple. I don't know.
Which is harder to stretch, a single bond or a triple bond?
Triple.
Triple bond, yeah. And so the triple bond is going to have a higher spring constant. It's going to take more force for that triple bond to stretch than it is for a single bond to stretch. And so these spring constants are going to be large for stronger bonds. Right? And so I'll just put in parentheses triple less than double. Greater than. For our reduced mass, we have an equation for that, right? Mu is equal to m1 times m2 divided by the sum m1 plus m2. Of course, this has to be in kilograms. And it's not in kilograms of molar mass. That's a common mistake, right? It's in kilograms of each individual atom or each individual thing that we're talking about. And so when we think about this, put it here in kilograms per atom. Right? And so we got to be careful about that, especially when you go to do those calculations. But when we do this, we get a spring constant of Newton per meter. So that's kilogram meters per second squared. And we divide that by meters, and then we divide that by kilograms. And so we get per second squared. We take the square root, and so we're left with hertz. Right, as our frequency. Now, we don't often think about things in terms of angular frequency, but we can always convert that over. Right, we can think about this as linear frequency by dividing by 2 pi. Right. And so nu, our linear frequency, is our angular frequency over 2 pi.
Dr. Davis, what is the new stand for again? Frequency?
Yeah, so this is our linear. Our linear frequency, and that's more like what we would plug into a E equals H nu kind of situation to figure out the energy of the photon necessary, for example. And so we just have to take into account that. So we can't plug, so let me write it out. E equals H nu, not E equals H omega. So we could write this as E equals H omega over 2 pi, right? That works too. But we can't plug in our angular frequency for linear frequency. When we do all of our sort of light equations, all of that wave mechanics kind of stuff, we always think about those waves as being in a straight line rather than being in a circle. And so the wave mechanics equations are all written with linear frequency in mind rather than angular frequency. Okay. If you've ever taken an infrared spectrum, and I sure hope you all have, what's that x-axis in?
Wave number.
Wave numbers, yeah. And so we need to talk just a bit about what wave numbers are, right? And then we'll talk a little bit too about the different regions of infrared frequencies. So a wave number is given the symbol nu tilde, right? And it's usually in units of centimeters to the -1. Now, physicists and chemists everywhere will say that that's frequency. Right? You know that that's not frequency. I know that that's not frequency. They still call it frequency because we can get a frequency out of it, but it's not frequency. But that's what they call it. So we will continue. So who has memorized an infrared transition?
3600.
3600. And what,
Alcohol.
yeah. Those of you that researched this summer probably said, uh-oh, there's water. If you saw a peak at 3600.
Is 2200 the C double bond O?
It depends. So in aldehydes, I think it's a little bit lower. But in carboxylic acids, I think it's about 1700.
Mm-hmm.
Did you say seven? What did you say? You said 2200.
I said 2200. I think there's something there. I just don't know what it is.
Yeah. Oh, there's something there for sure. Yeah, I don't do a lot of IR. I don't have these memorized. But there are some tables if you're curious. I'm not going to have you memorize them either. Quickly, let's convert this into a wavelength, an actual, we can do it in nanometers, but it's going to be a big number. So if you want to leave it in microns, either way. So this is the same as 1 over 3600 centimeters. How do I want to explain this? Let me erase. When we think about these energies and these frequencies, right? Going back to our energy equation, E equals H nu, but if we want to convert that frequency to a wavelength, it's H times C over lambda. And that over lambda is why we talk about wave numbers as being a frequency, right? 1 over lambda is part of the part of that substitution for frequency in our energy equation. And so when we do this, we can think about C in terms of centimeters per second. So that's times 10 to the 10 centimeters per second. And so E equals 6.626 times 10 to the negative 34 joule seconds times 3 times 10 to the 10 centimeters per second divided by 3,600 centimeters.
I always interpreted like the 3,600 inverse centimeters, like the 3,600 was on the numerator and the centimeters was on the denominator, but they're both together.
They are.
Okay. So we have 1 over 3,600, 1 over centimeters. Is how that's written?
Didn't we already convert to wavelength instead of wave number? We flip them?
Yeah, okay. Yeah, so I think the combination of your responses is correct. We did already convert to wavelength, 1 over 3,600, and it is centimeters. So yeah, you're right, Caroline. Yeah, it's like 3,600 times 1 over centimeter. Okay. So remember our cutoff for visible light was about where? Our exam on that's tomorrow. Do you remember the cutoff between UV and vis-ish?
It's like, don't we have a 2 to 400 and then like a 4 to 900
That
ish.
sounds good. Yeah. So 2 to 400 is UV. We can go a little bit lower than that sometimes, but 400 is a good cutoff point for our transition. It's a little more. It's not hard. It's a flexible thing because is 399 visible for everybody? I don't know. Is 398 visible for some people? Maybe. Right? Where's the cutoff between UV and Viz? I'm maybe somewhere someone has written a definition, but generally speaking, 400 is a good cutoff. And then yeah, somewhere around 900, maybe even 800, sort of depending on who you ask, is the cutoff for visible light before we get into that IR region. And so we're talking about 3 times that wavelength here. So we're firmly in the IR at 3600 wave numbers. Just for the sake of argument and for comparison, let's do quickly, if we were just at the edge of things, so let's say we're at 800 nanometers, convert that to centimeter to wave numbers.
Dr. Davis, did you say that UV was 200 to 400 and visible was 400 to like 800 or 900?
That's it.
Okay.
So we're going to a lower wavelength. Should that be lower or higher frequency?
Higher frequency.
Higher frequency. And so what'd you get? Should be a larger number.
$12,500.
Excellent. Yeah.
How did you calculate that?
So we got to convert nanometers to centimeters, and then we just do 1 over that answer.
Okay.
So again, just to clarify, so what we were talking about earlier, Caroline's question, this is the same as saying 1 over 3600 centimeters, right? Is when we talk about, this is our frequency, for lack of a better word. This would be our wavelength. Okay. The different spectral regions, I'm actually not going to get into too much just because the paper talks about it a little bit, right? But when we talk about IR, we're usually talking about 400 to 4,000 wave numbers. And then there's something called the near IR. It's, you know, closer to visible, so it's near us, I guess. I don't know. And this is that 4,000 to sort of 12,500 centimeter range. If there's a near IR, is there a far IR? Well, not really. You get into, you know, talking more about microwave spectroscopy and things like that as you get out past 400 wave numbers, and they start thinking about things a little bit differently. If you talk to microwave spectroscopists, they talk about it in actual frequencies, right, in terms of hertz and gigahertz and things like that. For infrared spectroscopists, they talk about frequencies in terms of inverse centimeters. And then for people who do electronic spectroscopy, UV vis, we talk about in terms of nanometers, right? We can't get our act together in terms of what we're actually trying to get across. All right, this is a little bit what we talked about earlier, how some functional groups have their own frequencies. Again, I'm not going to ask you to memorize this table. If you know some from organic, great. But the point that I'm trying to make here is that infrared is a useful tool in helping us sort of pick apart what a molecule, what functional groups a molecule might have based on the frequencies in that spectrum. And so, yeah, right here, this is supposed to be 3650, not 36,500. And so we have these different functional groups. Let's see, Caroline asked about 2200. It looks like triple bonds here, but maybe maybe we could find a carboxylic acid that's that low. I don't know. And you'll notice too that some of these frequencies are slightly different in different books and different tables. It's just which molecules you're going to use is sort of your standard carboxylic acid or your standard carbonyl in a ketone versus an aldehyde, right? And so what are you going to use as your standard, or are you going to take an average? And so you'll see slightly different numbers wherever you look, but this text uses a pretty wide window here for most things. As we get farther and farther out, right, these are very low energy because they have very low frequencies, right, wave number. Again, a weird thing about IR is that wave numbers are inverse on the x-axis. Right? We start at high wave number and go to low wave number. That's because really you're starting at low wavelength and going to high wavelength, right? And so, yeah, who knows? I wasn't there when they made the conventions. And so because we're getting into such low energy stuff, there are lots of sort of whole molecule vibrations that fall into this fingerprint region. That's why you have a whole lot of peaks that are largely unidentifiable for molecules, rather than these sort of very clean, very clear group frequencies. We get these non-group frequencies that are whole molecule frequencies that are very low in energy. If you think about a hummingbird versus an eagle, right? The hummingbird flaps his wings all the time. And so if we think about something like a OH group, he's out there wagging because that hydrogen can just move so quickly, right? But if we think about a whole benzene ring or something even larger, that whole molecule is going to move relatively slowly in terms of its vibration, just because there's a lot of mass moving. And so think more like an eagle for a benzene ring versus a hummingbird for an OH group. And so lots of those molecular frequencies are down at the bottom end. All right, so if we were in person, you'd get to see me dance this morning as we do these vibrations. Instead, you get a GIF. When we talk about normal modes, we're talking about sort of the standard vibrational, the standard ways a certain molecule will vibrate. And when we think about molecular vibrations, we have to think about ways in which a molecule can move. And the ways a molecule can move is based on the ways that its atoms can move, right? And so when we talk about normal modes, we're going to talk about degrees of freedom for motion. Right? Every atom that we have can move in three directions, right? X, Y, and Z. Every movement is some combination of those three directions. And so for a standard molecule with n number of atoms, there should be 3 times n degrees of freedom. This is X, Y, and Z for all atoms, or for, I'm going to say for n atoms. That's the total number of degrees of freedom. But there are some types of motion that aren't vibrations, right? There are types of motion that don't qualify as vibrational modes. And so if all of our molecules, all n atoms in our molecule are moving along the X direction, then that's a translation, right? Same with the moving along the Y or along the Z. And so if our molecule, we're going to use my cat treat container. If my molecule is moving in one dimension, right, that's translation. That's not rotation. He can move in this dimension or he can move in this dimension. And all three of those motions are translation, not vibration. So we subtract 3 for translation. Right. Now, if we move along a not axis, right? So if this is, X, Y, and Z, we could move this way, but that's just a combination of those 3 motions, right? It's a little step in this dimension, a little step in this dimension, a little step in that dimension. And we can break it down in terms of how it's moving. We can also take a molecule and we can rotate it around each axis, right? So if we rotate it this way, all those atoms are moving in sync, but it's not a vibration, it's a rotation. We can do this way, same thing. We can do this way, same thing. And so we can rotate around those 3 axes as well. And so we end up with 3n minus 6 vibrational modes. But wait, what if we have a linear molecule, right? This linear molecule, if it's rotating around this axis, nothing's changing. Okay? And if nothing's changing, then quantum mechanically speaking, you're not really rotating, right? Because think about those atoms. Those atoms are constantly, the electrons are constantly in motion anyway. What does a rotating atom really look like, right? That nucleus is constantly moving. Those electrons are constantly moving. There's really no such thing as a rotating atom, right? And so if we have a linear molecule, there is no rotation along the line of the bond axis. We usually sort of defer that to be the z-axis, but it doesn't really matter here. And so for linear molecules, we lose rotation. So we end up with 1 extra vibration for linear molecules. And so water has 3 atoms. 3 times 3 is 9. So water should have 3 vibrational modes. 9 minus 6 is 3. And so here in our little animation, you see the 3 different vibrational modes for water. We have this antisymmetric stretch, asymmetric stretch, where the 2 hydrogen atoms are moving opposite one another relative to the oxygen. We have the symmetric stretch where both of those bonds are lengthening or shortening at the same amount, the same ratio. And then we have this bend, this scissoring. And so those 2 hydrogen atoms are moving closer and farther apart to one another. Their actual bond length isn't changing. What about for something like carbon dioxide? How many vibrations should carbon dioxide have? 3, says Annabelle. It has the same number of atoms, but what do we know about carbon dioxide?
It's linear.
It's linear. So Annabelle's going to change her answer to 4. Excellent. Yeah, so CO2 has 4 vibrational modes. Right? I'm going to try to draw them here for you. If I keep the C in the fixed position, how would you classify this? Is this as one of these 3? Is this antisymmetric, symmetric, or a bend? It's the first one. It's antisymmetric. Right. I'll be honest with you, I stole this off of the Google somewhere. I've never called it antisymmetric. I've always called it asymmetric. Our textbook also calls it asymmetric, so I'm going to write asymmetric. Okay. We have another one that might look something like this. What's that? That's the second one. That's our symmetric stretch. Okay. So this is more like a bend, right? We don't call this one a bend because it's going around the center of gravity. In the water one, right, it's only on one side of the center of gravity, like a pair of scissors. Right? This one is we call this a wag, right? Because it's sort of going on either side of the center of gravity. How else can we move those atoms around? We need a 4th vibrational mode.
A wag in the other direction wouldn't count, right? Because you could just rotate the molecule and it would be the same thing.
So if
you went like that.
Yeah, so in and out of the plane is our 4th one. Absolutely. If we rotate the molecule, then we're changing its orientation. And so the thing about vibrations is that you can have multiple vibrations at the same time, right? And so we have to hold our molecule still in order to experience multiple vibrations at the same time if it's the same vibration in multiple directions.
Yeah.
So we can have, I'm going to draw it with our dots and dashes like we see in organic. So we call this one an in-plane and an out-of-plane. If you ever see OOP, that's what it stands. That's out of plane. Now, tell me something that might be true about these two vibrations, these last two. You think it takes more or less or the same amount of energy to do in plane versus out of plane?
The same.
The same, absolutely. And what do we call two things that have the same energy?
Degenerate.
Degenerate, yeah. And so how many peaks for CO2 are we going to see in our infrared spectrum? Just 3, yeah. And so it might be easy for us to think that we have 3 vibrations. Interestingly, what we actually get when we do both of these at the same time, right? Remember, if it's degenerate, then it's the same energy. So if I put in just that amount of energy, I can't excite one of those over the other one, right? I'm going to excite both of those at the same time. And so what ends up happening, I don't know if I can do this very well, but here's our CO2 with our carbon in the middle, right? What ends up happening is we have our out of plane and our in plane. And so if we do both of those at the same time, we sort of get a what do you want to call that? I don't know. Well, the scientific word is a Coriolis, right? We end up making a circle in the middle rather than a line in plane, sorry, a line out of plane and a line in plane. We end up making this circle. How about I do this? Can you see this better? Right. And so my oxygen atoms end up not moving very much at all. And my carbon atom is getting sick on the teacups, right? And so that's called the Coriolis effect, or Coriolis vibration. Okay. And so I'm not going to ask you to do a molecule that's more than, I don't know, 5 atoms or something. And the only reason I say 5 is because this next slide is CH4, right? This is methane. It has it has 5 atoms. 5 times 3 is 15. 15 minus 6 is 9. And so of those 9 vibrations, some of these are going to be degenerate, right? Some of these are going to have multiple degenerate vibrations. One of the things that I want to point out, right, it's using dots and dashes, sort of like I did before. We have the wagging, the twisting, right, where one set, there should be an arrow going up here. The torque. This one, the way they've drawn it, kind of looks like it's just a translation, right? But the carbon atom is not moving, right? So those 4 hydrogens are all sort of rocking around it. They're not, the carbon atom's not moving. But again, I'm not going to ask you to sort of memorize these and tell me what they are. I think that's kind of pointless. But being able to calculate the number of normal modes in a molecule and then thinking about sort of what they might be, especially for small molecules. Names I don't care about so much as how the actual atoms move. Okay. All right. Well, we're gonna stop it there. I guess the lecture will be on Fourier transform, and then Friday we'll pick up with instrumentation bits and bobs. Okay. I hope you have a glorious day.
Dr. Davis, is this stuff going to be on our test?
It will not be.
Okay, so we ended the last chapter 8.
That's right.
Okay.